Hi there. In response to a couple of comments I received on a video I've recently put up from an AQA paper, A-level paper on implicit differentiation, a couple of comments basically said that that 13 marks was a gift, and they would have been blessed if it was in an Edexcel paper, suggesting probably that the Edexcel questions might be a bit more difficult. So for that reason, I dug out a similar question worth 10 marks rather than the 13 for AQA, so obviously a slight disparity there. But aside from that, there didn't seem to be a huge amount of difference, apart from context. But I'm going to jump straight in on the first part, which is simply to differentiate the implicit function term by term. So 2x minus, now in brackets, we use the chain rule. So it's going to be 2 multiplied by y plus 2x dy by dx plus 6y dy dx equals 0. Okay, so pretty straightforward term by term. Obviously I'm going to expand the square brackets out, so we get another 2x minus 2y minus 2x dy by dx plus 6y dy by dx equals 0. And collecting our dy dx's together, and then obviously moving everything to the other side, we end up with dy by dx brackets, so we get 6y minus 2x, so combine these two terms and factorised, equals 2y minus 2x. Okay, so pretty straightforward so far. Dy by dx is equal to 2y minus 2x all over 6y minus 2x. And obviously that simplifies down, dividing every term by 2, so I'll end up with y minus x over 3y minus x. Okay, and that was the required result. So first part, pretty pedestrian. Okay, so derivative's been done. That was actually worth 4 marks. The next bit is worth 5 marks. And that is to establish the coordinates of the vertical tangents to the kind of, it's almost like an ellipse on its side. We've got 2 vertical tangents at points P and Q, and that is basically that function there. So the one on the right should be more vertical, but it will suffice. So what we're basically looking for is an infinite gradient. So we're not setting the derivative to 0 at this point, because of course that would involve the horizontal tangents. So the vertical tangents, we're basically saying that dy by dx tends to infinity. Okay, and if that's the case, y minus x over 3 minus x tends to infinity, and that would happen if 3y minus x tended to 0. So what we're going to do is we're going to get the extreme case, obviously, and we say 3y minus x equals 0, and therefore x is equal to 3y. So we've now got a relationship between the two, and all we now need to do is plug in our substitution. So 3y in place of x, so in this case it would be 3y all squared minus 2 lots of 3y times y, so I don't make any mistakes, I'm just putting in brackets, plus 3y squared equals 50. And we can solve for y quite straightforward. 9y squared minus 6y squared plus 3y squared equals 50. So really, really straightforward if you get the asymptote, or rather, sorry, the vertical gradient of infinity. And collecting the terms together, we end up with 6y squared equals 50, or y squared equals 50 over 6, or 25 over 3. So taking your square root both sides, we get 5 over root 3. Remember that's positive or negative, so there's our 2 values, one here and one here. I'm going to tidy that up a little bit, and it's going to be plus or minus 5 root 3 upon 3. Okay, so there's our y value, and we've got a really basic relationship between x and y. Our x values are simply 3 times this, so therefore we've got plus or minus 5 root 3. Okay, so combining these two, our coordinates are negative, so get this the right way round, 5 5 root 3, comma, negative 5 root 3 upon 3, and also just positive 5 root 3 and positive 5 root 3 upon 3. So those are our two coordinates for P and for Q, or rather the points at which it touches the function. Now, this I looked in the mark scheme because I actually thought about something else, or a different way of actually doing this, and it wasn't in the mark scheme. So if I were to, let's rub this out and give myself a little room, okay, I could have gone down this route. So, of course, instead of finding dy dx, I could actually invert that, find the reciprocal, and basically set dx dy equal to 0. And that would give me the vertical lines that we were looking for, i.e. 3y minus x over y minus x equals 0. And we end up with exactly the same result. Okay, because obviously if that tends to 0, then 3y minus x must be 0. And we end up with the same result as we had before. Okay, but actually conceptually a little easier, I think. And finally, the one mark at the end was to establish how would you, and it's only worth 1 mark, how would you work out the top and bottom extremes of the function, i.e. setting the gradient to 0. So to do that, I would simply say dy by dx equals 0 to find the horizontal tangents, i.e. Y minus x over 3y minus x is 0, and therefore y equals x, and sub that into there. But it doesn't actually ask you to prove anything, it just asks you to explain how. Okay, so there's your final mark of a pretty straightforward 10-mark question.